Okay, so far we talk about how to culture the mammalian cells for the last class. So today we talk about the protein absorption, because the reason from the classes we had before was that the mammalian cells adhere onto surfaces, right? Adhere onto surfaces. But the surfaces has to have the proteins layers, and it must have protein layers and surfaces. So that I was emphasizing when I explained the serum protein. Then in a media you have a serum. The serum has a lot of proteins absorb on surfaces, and the mammalian cells recognize proteins and they attach to it. So that is how the key mechanisms mammalian cells grow. That's why we used trypsin to cleave the proteins that is on the surfaces, and then cells are detached from the surfaces because of the trypsin action, and then we counted the cells and we go to the next step for culturing the second subsequent culture. So that's why the protein layers is very important. But how to analyze protein layer? How to analyze protein layer? Because it's very thin. Remember the size of the biomicromolecule in the really first class and the second classes. That if this is surfaces, then proteins are maybe absorbed on here, but the dimension is generally 2 to 3 nanometers. If proteins can possibly have a multi-layers depending on the concentration of the solution, but still probably 5 to 10 nanometers at best, then they form on surfaces. So that generally speaking, it's very difficult to distinguish between, say, if this is the collagen solution, and then you've got a piece of glasses that for the mammalian cell culture, and then you dip it in and take it out, and this is now coated glass. Then by their appearance, basically, their appearance is the same, because of the layer, the protein is very thin, and also, of course, protein don't have any color, right? So it's all transparent glasses, even before and after. So there's the questions that you have a two piece of glasses. One is uncoated by the protein, one have a protein coated. And how you can distinguish? The answers might be based on your knowledge that you put it into the mammalian cell solution. The mammalian cell of course, media doesn't have a serum because serum has a protein. So in serum-free media, in mammalian cell, one surface has a protein absorbed, so mammalian cells can go and attach, adhere, grow. The other one doesn't recognize no cells. So that is kind of thing. But this is not a chemistry, right? This is not a chemistry that is a biological way to distinguish the surfaces with the proteins or no protein. But there's a way actually you can analyze the proteins. So that is we called some surface sensitive technique. So the XPS we call this X-ray photoelectron spectroscopy. That is a very surface sensitive analysis tool. This is the surface sensitive analysis tool. And the important information I give you right now is they detected chemical compositions at very surfaces at the levels of about the 15 to 20 nanometers, about 15 to 20 nanometers in thickness. The reason is why they such a sensitive in surface analysis is that because of the nature of the photoelectron. The photoelectrons is not here. So the photoelectrons is, for example, you have some materials, and the easiest materials is aluminum foil. And then you actually got illuminations by the light. Say some little bit shorter wavelengths, higher energy UV. Then actually you can see the phenomena that electrons comes out from the surfaces. This is called, generally speaking, photoelectron. We provide a photon, and then electrons coming out. Photoelectrons. So that is, these photoelectrons are very specific energies. They're very high specific unique way of binding energy. Generally speaking, you can think about it. I mean, if the energy is you provide it into the materials, and then there's a kinetic energy because they fly away. So there's kinetic energy of the photoelectrons because this is mass times velocity square, and then binding energy that electrons are some orbitals, they're binding, so they have to take out from this orbital binding energy. It has to be higher, the energy provided by the light. So then, generally speaking, in the some constant of the overall mechanical configurations plus binding energy and kinetic energy is the energy provided. But we can experimentally measure, because we can experimentally measure the kinetic energy, such as the velocity in here. So we can actually measure this guy, right? So this guy, and then that energy provided, and minus binding energy, and minus R. So anyway, this is constant, so you can ignore this one, generally speaking. So the kinetic energy measure, which is the energy that we measure by some conducting materials using this electron, and then that can be detected, and then you see you provided this environment is a vacuum because you have an air, then oxygen, nitrogen, you can collide each other, so you can bind each other, so the energy is loosed, so you can actually distort the kinetic energy if there's a gas molecules as existed. So you can take out the vacuum, then there's no obstacles here. And then the sensitivity of this is the same because the electrons can be collided with other materials, the atoms and electrons. So then if you can think about this, any given materials here, and then X-ray comes in penetrating through these materials, but at the same time, all this pathway, all the pathway that X-rays are, or photons, penetrating through, providing actually all photoelectrons. But the problem is the photoelectrons generated from very deep inside the materials. Actually, these materials is also actually covered by the neighboring materials, neighboring atoms, basically. They can actually escape, hindering their escape of the electrons. So they can actually hit, then goes different way. These electrons can generate it, but they can collide it to materials and then they cannot escape it. So only photoelectron generated very, very surface can escape. So that thickness level is about 15 to 20 nanometers. So that's why this overall this X-ray photoelectron spectroscopy is generally surface sensitive techniques that must be Otherwise, it cannot do this right. This is a spectroscopy, so that is quantified. This is quantitative tool. Quantitative tool. It's not a qualitative tool. So qualitative tool is called the spectrometry, not a spectroscopy. So the mass is basically spectrometry because the ionization process is not a quantitative behavior. It's just qualitative behavior. So NMR is a spectroscopy. You can count, you can compare the amount of the molecules. FTIR is a spectroscopy. X-ray, photoelectron, this is also spectroscopy. You can actually see later on that how much carbon you have, how much nitrogen you have, how much sulfur you have, oxygen, phosphate you have. Okay, so this is spectroscopy. So this generally the X-ray photoelectron spectroscopy is a very good technique for analyzing the protein absorption samples. In this case, if the previous cases that I explained is you have a glass with proteins absorbed on it, like 5 nanometers, for example, then this glass is basically silicon oxide. So you have Si and oxygen you have. This one protein you have a carbon, nitrogen, oxygen, sulfur from the cysteine. Then X-rays coming, all the electrons that not only the protein level but also the substrate level from the glass. So you can expect it to see photoelectrons of Si from the glass and oxygen from the glass, oxygen from the protein, carbon from the protein, nitrogen from the protein, sulfur from the protein. This is what you expect to see. And then generally you have, say, the binding energy. Binding energy from the 0 to 1 to 1100 electron volt. Generally speaking, this is the energy area of the X-ray that we provided in commercial XPS. Then you have the carbon, nitrogen, oxygen, sulfur, silicon, and a very sharp peak at the throughout this technique. So the carbon is, especially in this binding energy level, you have 1s orbitals that we easily detected. Then also nitrogen case is 1s orbitals. Oxygen is also 1s orbitals. Silicon is 2s, also 2p. You can have a separate peak. Silicon, I'm sorry, it's Si. Maybe S is generally speaking 2p. So that is kind of range that we detect, and then depending on the height, the overall area under the curve, that is a spectroscopy. So that how much this portion and this portion is twice of this, twice of that, and then this is spectroscopy technique. So the higher peaks, then the higher amount of the atoms we have. So this one is the XPS, the instrument configurations, overall configurations of XPS. So it looks very complicated, but it's very simple. For example, your protein absorbed surfaces are located here, and then there is the X-ray source that's coming from here, and then you got now the X-rays are hitting on surfaces, and then basically the all photoelectrons are ejecting in all different directions. So from here, any directions is possible. But collecting this aperture, that electrons are coming from this, only electrons, part of this electrons coming from here, because this positive charge is applied in here. And then they analyze this detecting these photoelectrons here. So basically, they analyze the kinetic energy, which is the speed. So you have an input energy, and then there's a certain amount of energy is consumed, and then the rest of the energy is basically the electrons are binding energy, their own levels of binding, but has to be the binding energy has to be input energy has to be larger than the binding energy. So the total energy is binding energy plus the kinetic energy plus there are some consumed energy levels that is configured due to the configuration of this instrument. So total equals to the kinetic energy of these electrons, their binding energy, which is we measure, and then there are other factors. So that is you can understand by this way. This one is electron gun. The electron gun is basically you have ejecting the electrons from the materials, then the overall charge of the material should be positive, and then becomes a problem because you keep ejecting the photoelectrons and becomes more positive and more positive surfaces provided. So that's why the electron guns making the surfaces neutral. So this is very important. Neutral surfaces has to be stabilize all the systems that we analyze properly. So this is neutralizing electron guns. And other things are basically the computer systems and the vacuum. The vacuum has to be very, very high in this chamber. Because if there's a gas molecules are a lot, then the electrons actually heated by the gas molecules, and then the kinetic energy, which is what we measure through this instrument, has to be changed. So if there should not be no gas molecules, that is increasing the probability for the photoelectrons actually heated by this gas molecule. So in the vacuum level is typically 10 to the minus 11 or 10 torr, which is very, very low, ultra vacuum level. So that's why it takes some time actually to stabilize the system before the analysis of operating the XPS technique. So then I'll skip many of this, then I'll come back on this. First, I think I should show a real example. That is how make you used to understand this the system. So this is the some sort of ketone, ethyl ketone structures. This is polymer. You have repeating this. You can imagine repeating these structures. Then you have a carbon and oxygen. There's no nitrogen, no sulfur, no phosphate. So look like this. You take all the materials and cut piece of it, and then you clean on surfaces because there's a dust always in there. You don't want to analyze the dust because this XPS is very, very surface sensitive technique. So you clean very well, then you put it into the XPS and you do it. Then this is what you get actually from this samples. So say because you have carbon and you have oxygen, then you have a carbon photoelectron peak in here. We have oxygen photoelectron peak in here. So this is all two. It's very simple, but the important thing is there's all fixed energy. This is what we know at the introductions of XPS. This is if there's an orbital 1s, 2s, 2p, 3s, 3p, then carbon for the carbon 1s has to be fixed binding energy of the electron level. If a nitrogen but different value, but there's a fixed energy. But in the case of carbon 1s, we have about 284 binding electron volt binding energy, which is this peak. And a little bit over than 500 electron volt, you have oxygen. So this is very clear. So if you have a number of this, then you have a carbon. If this is only particular number of this, it is oxygen. You have titanium here, iron here, sulfur here, gold might be here and here. They're all fixed energy. So you have actually library book. You can actually see or by the Google or internet, then you can find which atoms and which orbitals even you can actually pinpoint it. And the analysis basically is easy task. And now a little bit deeper. So this is the previous the data that I explained. So now you can zoom in for each peak. This is the carbon 1s, the electron photoelectron from the carbon 1s orbitals. This is the photoelectrons from oxygen 1s orbitals. Then you see now for the carbon, which is this part, this is 280, about 284, and the other peaks. So now you see, if you zoom in this area, then you have several different peaks you can find. So you can this is type of the microenvironment of this materials are the carbon is different. So for example, you have imagine the environment of the bonding neighbors. Say this carbon, for example, has the carbonyl bond, which is the O minus delta minus, so electrons are actually hitting into here. And also this carbon also, the other electrons are crowded heading into this direction, because the oxygen is more electronegative. So this carbon is very electron deficient cases. And also this carbon is nearby the oxygen. So but not this level, but there's a electron negative atom right next to it. So there's some influence from this carbon. But however, this carbon has no influence. There's no carbon and the hydrogen, so there's no influence. So the XPS, you analyze it right next to the carbons. The NMR cases, generally speaking, NMR cases you have a splitting, then you have a 3 carbon rules, right? 3 carbon rules, but XPS is only 3 bonding rules in NMR. But the XPS you have 1 bonding rule, just the nearby atoms. Okay, so this is carbon, this is oxygen and carbon, but oxygen is dominant. Okay, so I will continue this for the XPS explanation for the next classes. Okay.